Hello everyone, welcome to all. Myself Dr. Indrani, Department of Electronics and Instrumentation Engineering, SRM Institute of Science and Technology. Today topic is microfabrication process. Under the microfabrication process in MEMS, photolithography, ion implantation, diffusion, oxidation, chemical vapor deposition, physical vapor deposition, deposition by epidoxy, etching. Photolithography. Photolithography is electrical process in the fabrication of micro-electromechanical systems. It is used to transfer the geometric pattern from a photomask to a substrate, which is typically a silicon wafer. The process is similar to that used in the production of integrated circuits, but it is adapted to accommodate the three-dimensional structure for larger feature size often found in MEMS devices. Photolithography is a light stone writing. It is an optical means of transferring pattern into a substrate. As many as 10,000 transistors can be fabricated on a 1 cm into 1 cm chip. The conventional photolithography process uses UV and device dimension as small as 2 micrometer can be obtained. Nowadays, using X-ray or electron beam lithography techniques, the device dimension down to sub-micron range is less than 1 micrometer. This is a general procedure for photolithography process. That process initially substrate is there. On the substrate photoresist material should be placed. Then after that we go for the UV light. By using the UV light through mask, that light rays falls on the substrate. The important process in photolithography for development, etching, photoresist removal. Key steps in photolithography for MEMS. Substrate preparation. This is the first step. The silicon vapor is cleaned to remove any contaminant that could interfere with the photolithography process. Next, photoresist application. A layer of photoresist, which is a light sensitive material, is uniformly applied to the surface of the wafer. This is usually done by spin coating, where the wafer is spun at the high speed to ensure a thin, even coating. Soft vacuum. The wafer is then soft vacuumed to evaporate the solvent in the photoresist, improving the adhesion and photoresistivity reactivity. Next one is exposure. The exposure means the photoresist coated wafer is aligned with a photomask which contains the desired pattern. The wafer is exposed to ultraviolet light, which changes the chemical structure of the exposed region of the photoresist. Photoresist are two types. One is a positive photoresist and negative photoresist. The meaning of the positive photoresist is the exposed region become more soluble in the developer solutions. Negative photoresist meaning the exposed region become less soluble the developer solution. Next is development. The wafer is developed using a chemical solution that removes the more soluble region of the photoresist, leaving a pattern that matches the photomask. Next is the hard packing. The developed wafer is hard packed to harden the remaining photoresist and remove its resistance to subsequent process. Photoresist removal next. After etching, the remaining photoresist should be removed, typically using a chemical stripper or plasma etching. What are the equipment used in photolithography? Spin coater, mask aligner, UV exposure system, developer system. By using spin coater to apply a uniform photoresist layer in the mask aligner for precise alignment of the photomask, UV exposure system to expose the photoresist, development system to develop the exposed photoresist. Photolithography technique, contact printing. Contact printing means direct contact between the mask and the substrate. Proximity printing, next a small gap between the mask and the substrate. Next one is projection printing, using the lenses to project the mask image onto the substrate. What are the challenges in that photolithography for MEMS? First one is resolution limitation, difficulty in achieving very small feature size. Next one is aspect ratio. Aspect ratio maintaining the depth and width of the ratio of features. Next, defects, minimizing the defects due to the particles or imperfection in the mask or photoresist. What are the challenges? Next one is the process integration. Photolithography in MEMS must be integrated with other fabrication process such as doping, deposition and bonding to create a complex devices. Photolithography remains a fundamental technology in MEMS fabrication, enabling the precise patterning, the structuring of micro-scale and nanoscale devices used in a wide range of applications, from a sensor and actuator to optical and biomedical devices, etc. What is a comparison between positive photoresist and negative photoresist? Positive photoresist used material is PMMA. In negative photoresist, two components bits rubber is also used. The second comparison, the two component equivalent resist involving diazonistor in negative photoresist Kodak KTFR, that is a material, and positive photoresist sensitive to UV light. In negative photoresist more sensitive to electron beam. In positive photoresist, most positive resist can be developed in alkane solvents such as potassium hydroxide head-ons. In negative photoresist, ethylene is the most commonly used in solvent for developing the negative photoresist. The next topic is ion implantation. It is a technique used to introduce the impurities to a silicon wafer. Ion implantation is a micro electromechanical system, refers to the process of introducing ions into the surface of the MEMS devices to modify their properties. Next, the technique is used to enhance the various characteristics of the devices such as electrical, magnetic, mechanical and tribological properties. Here is an overview of the key aspect of the ion implantation in MEMS. Purpose of the ion implantation: magnetic properties, mechanical properties and electrical properties. Magnetic properties: adding ion can impart the magnetic properties to the non-magnetic material, enabling the creation of magnetic MEMS devices. By using the mechanical properties, ion implantation can increase the hardness and wear the resistance of the MEMS components, improving their durability. In electrical properties, it can be modify the electrical conductivity of the surface, which can be useful to certain sensor application. Next, ion implantation. Ions are accelerated and directed towards the MEMS device surface in a controlled manner. The ions penetrate the surface and embedded into the material. Next, the doping concentration of the ion implantation. The concentration of implanted ions is carefully controlled to achieve the desired modification without compromising the structural integrity of the MEMS devices. This is a major block diagram for the ion implantation. Next topic is diffusion. The process of doping, that is adding the impurity to the silicon wafer, is called diffusion. This uses a high temperature furnace, giving a plot temperature profile over a useful length. Diffusion means a quartz board containing cleaned wafer is pushed into the hot zone with the temperature maintained at 1000 degrees Celsius. Impurities to be diffused are rarely used in their elemental forms. Compounds are like boron oxide, boron chloride are used for the boron and phosphorus. Phosphorus pentoxide, phosphorus oxalochloride are used as a source of phosphorus. A carrier gas such as dry oxygen or nitrogen is normally used for sweeping the impurity to the high temperature zone. The depth of the diffusion depends upon the time of diffusion, which normally extends to 2 hours. Advantages of the ion implantation: performed at low temperature. In diffusion, temperature has to be controlled over a larger area inside the oven, whereas here accelerating the potential and the beam current are electrically controlled from outside. Disadvantages of the ion implantation: the dopant distribution in the substrate is less uniform. Next topic is oxidation. The oxidation meaning the process in which a thin, thick layer of silicon dioxide formed on surface of silicon wafer using the thermal growth technique is called oxidation. The facility of the thermal oxidation of the SiO2. Silicon react with oxygen produces silicon dioxide. Silicon react with water produces silicon dioxide plus hydrogen gas. Deposition by epidoxy. Epidoxy is the extension of a single crystal substrate by growing a film of the same single crystal material one may deposit the gallium arsenide to gallium arsenide substrate using this technique. Next, epidoxy deposition methods. Various type: vapor phase epidoxy, molecular beam epidoxy, metal organic CVD. CVD means that is a chemical vapor deposition, complementary metal oxidation of the semiconductor epidoxy. This is a diagram for reactor of epidoxy deposition. There are two types, one is horizontal, other one is vertical. Next topic is etching, most important process in microfabrication. It involves the removal of material in desired areas by physical or chemical means. This etching, there are two types of etching: physical etching, chemical etching. Physical etching we call it dry etching, chemical etching we call it wet etching. The wet etching are divided into two groups, one is isotropic etching, other one is anisotropic etching. Thank you.